Alrighty, as we finish up section 7.3, we've got problem number 4, talking about carbon dating. Carbon dating is used to determine the age of fossils, given the fact that carbon-14 decays at a continuous rate. So again, we see that continuous word, which tells us, sure enough, that we've got an E in our function that describes it. So the function used to describe the amount of carbon-14, Y in grams, present at any given time, where X is in years, is the function y equals 20e to the negative 0.00121x. And in part A, we want to know how much carbon-14 was present in the fossil after 100 years. Well, that's a value for x that we can plug in. So we just plug it straight into our equation, y equals 20e to the negative 0.00121 times 100. And again, we make our calculator do the heavy lifting on this. We plug everything in exactly how we see it, and we get 17.721-ish grams. So after 100 years, we're still looking at over 17 grams left. Well, if we're talking about fossils, we have to consider what happens after 15,000 years. So when we plug in x equals 15,000, we are going to get a number that's super small because we have exponential decay. So 121 times 15,000. Oops. And sure enough, our calculator spits it out using that E function, like capital E. So we have 2.622, and then it tells us E negative 7. Well, that's like saying times 10 to the negative 7th, which times 10 to the negative anything is usually a really, really small number. And sure enough, it's 0.000002622 grams, which to us seems insignificant, but after 15,000 years, we want to be as precise as possible, and we like to keep as many decimals as we can because that's how carbon dating works. That's how we know the difference between a fossil that's 15,000 years old and 20,000 years old or 30,000 years old, etc. And then in part B, we want to graph the function and provide a sketch below. We want to know, when does the amount of carbon-14 in the fossil reach just 5 grams? Well, in order to do that, we are going to go to our y equals, and we're going to let y1 be that function with our x still in there. So y equals 20e to the negative 0.00121x. Make sure that you've got your negative sign and not a minus sign. And then we want to know when it's equal to just 5 grams. Well, that's a value for y. So what we do is we plug in y2 equals 5, and we are going to use our second trace feature. Now, first, knowing that we're talking about exponential decay, we know our y max just needs to be a little bit above 20 because it's going to be decreasing. I like to include a little bit of negative on our y-axis. Same thing with our x-axis. We had a question relating to 15,000 years later. And when it was at 15,000 years, we had less than 1 gram left. So I didn't feel the need to go that far out. I just went up to 4,000. Again, giving ourselves a little bit of negative. X scale by 1,000. And we get our two graphs that look like this. So our curve is that exponential decay function, and then that y2 equals 5 is that red line. Then we use our second trace intersect feature, which is option 5, and it'll ask you, hey, first curve, and I'll highlight the exponential decay. You say yes, enter. Second curve, question mark, yep, y2 equals 5, and then it makes you guess. We end up finding out that they intersect at 1145, or 0.6978, 5. So we knew the y-coordinate would be 5, and that's why we want to use our second trace feature. And then this gives us our time in years. So we'd provide a sketch below and make sure to include your windows. Our final answer then would be after 1145.7-ish years. Moving on to section 7.4, that was when we learned about logarithms. So we need to be able to rewrite logs, evaluate logs by hand and with our calculator, solve for inverses, and graph logs. So in problem 5, we are just rewriting each of these. And if it's given to us an exponential form, okay, if we have an exponent, we want to end with a log. So that's when we log loop it. It'll be log base 5 of 125 equals 3. Example B, we log loop it. We want to end with a log. So we have log base 2 of 1/16 equals -4. In C, I have an exponent, so I want to end with a log. So I draw my L. Log base E, I can write it as log base E of 1 equals 0. More typically, we'll see it ln, log natural, of 1 equals 0. And in D, this time they give me a log, so I want to end with an exponent. So I have 7 to the second equals 49. And sure enough, we know that to be a true statement. In E, they did not give us a base for a log, but we know that there's always an invisible 10 there if we do not see one. We have a log, so we want to end with an exponent. So 10 to the third equals 1,000. Again, that makes sense to us. Now we have a log, we want to end with an exponent, so we have 2 to the 9th equals 512. Now in G, it's a little bit tricky because they did not give us the base of the log, even though we know it to be E. And when we draw in our E, we have, okay, this E to the second equals E to the second. And to us, that seems strange to write that because it's redundant, and yeah, it makes sense, but it's true. And so all we were asked to do is rewrite it, so that's what we will do. And lastly, we have a log, so we want to end with an exponent. 11 to the -2nd is 1 over 121. Now, we can rewrite them, and that will help us evaluate our logs. So in 6, problem number 6, we want to we want to evaluate it. And in order to evaluate it, we first set it equal to x, and then log loop from there. So I have a log, I want to end with an exponent. So I have 3 to the x equals 81. And this is something where we need to be able to stop and think about it and confirm our result. Well, if we can't remember our powers of 3, we've got 3 to the first is 3, 3 to the second is 9, 3 to the third is 27. Well, yeah, 3 to the fourth is 81. And so confirming using our calculator, we would plug in 4 for that x. So 3 to the fourth, does it equal 81? Yep, it sure does. And in example B, again, set it equal to x and log loop it. 4 to what power gives us 1 over 64? Well, I know that 4 to the third gives us 64. In order to move that 64 to the denominator, we just make our 3 negative. So 4 to the -3rd is 1 over 64. So that must mean that the log base 4 of 1/64 is that -3.